So let's get started. Welcome you all again. So in the last class we looked at the Reynolds stress equation that we applied to a plane co-ed flow, and we saw the role of pressure strain rate term, right? So for that we took this plane co-ed flow and applied the conditions. We saw that the pressure strain rate term is responsible for this redistribution, and using continuity equation we showed the continuity equation for fluctuating velocity. We showed that this is the term which is actually stealing turbulence from the direction where it is produced and giving to the directions where it is not produced. So you may have a flow where production is dominant in all the three directions, and redistribution will also be active in all the three directions. Production rates may not be equal in all the three directions, but in the simplest configuration that we have taken, where production is there only in one direction, we have still seen that redistribution acts to give away turbulence to the other two directions. Okay, fine. So now I mentioned long back that we are going to use Reynolds stress equations as the way we derived, because it involves less number of unknowns. And somebody asked me, what is the other equation? Okay, so this is not useful for modeling community, but for completeness I am going to just give a note. If you are interested, you can do this as a homework. So note here, if you want to derive this Reynolds stress equation, and another way, starting again from first principles, okay, Reynolds stress equation, okay, derivation from another starting point. So what is that? Is that we take this fluctuating momentum equation, right? So we started with an equation for fluctuating velocity, we multiplied it with another velocity, another fluctuating velocity, right? And then we averaged it to get a Reynolds stress equation, correct? So we start with that one. Only thing is, here we write it differently. So the fluctuating momentum equation, this equation will be slightly different than what we have used. So I have the left hand side is same, plus uj bar dou ui prime by dou xj equal to, the pressure term is same. The one new term which is different is this particular term, dou by dou xj tau ij prime minus, you have uj prime dou I bar by dou xj minus of uj prime dou ui prime by dou xj minus uj prime dou I prime by dou xj. This was an average term. So if you compare this particular equation with the equation that we have used, you will see that the only term that is different is this particular term. Every other term is the same. We just multiplied this with another fluctuation, right, uk prime, and then averaged. We proceeded like that, the starting. This particular term was different because here we already used the incompressible consideration, right? So the tau ij prime here is nothing but your 2 nu sij prime. So we did use this condition that it is dou ui prime by dou xj plus dou uj prime by dou xi. So we use this, and then we said by continuity one of the term will go away. So we already used this as a simplified term, and therefore less unknowns resulted. So if you use this particular starting point, where don't use the incompressible flow consideration, just use dou by dou xj of your tau ij prime, and you continue, you will get two extra terms. The two extra terms, where does this viscosity term? This is essentially the viscous term, right? So viscous term is the different in both the derivations. So where does viscous term affect in the Reynolds stress equation? Sorry? Dissipation, right? There is a viscous dissipation rate, and what does viscous term do? Sorry? Yeah, that is the dissipation rate. So the viscous term here, this we split it into two parts, and then it goes into two different terms. Diffusion, right? So viscosity transports turbulence, viscosity also dissipates turbulence. So we saw that it splits into two terms, right? Therefore, this particular term, when if you continue to derive, you will get, it will affect both the viscous dissipation rate and the viscous diffusion rate, which will have much more unknowns than what we have got. Okay, so this affects both viscous dissipation rate and viscous diffusion rate. So this leads to far too many unknowns, more than what we have, and therefore this, if you continue to derive, you will get more unknowns here. Okay, so by continuing to derive Reynolds stress equation, using this star, you will get more unknowns. More unknowns in the viscous terms. Therefore, modeling community will not use this, will not proceed in this direction with this equation. We will continue to use what we have derived. It has less number of unknowns. Okay. So this is just a note. You can take it as a homework. If you are enthusiastic, you can go ahead and derive. It's not complicated. Same technique as we did. You can see that it leads to more unknowns. Okay. So we will come back to our original Reynolds stress equation and see that we can derive another equation from it, which is very useful for the both to study turbulence as well as for modeling. Okay, so this is what we call a turbulence kinetic energy equation. Turbulence kinetic energy, small k, equation. So if you look at by definition of this k, okay, it's also sometimes in literature referred as turbulence kinetic energy as TKA, or k is defined as half of ui prime over bar. Now how is this an energy? I said this is the, obviously I have ui prime, so that means this is sum, right, repeated index Einstein summation. So this is sum of three terms, three normal stresses that we discussed where redistribution is occurring, right. So this is the u1 prime bar plus u2 prime bar plus u3 prime over bar. Sum of three normal stresses, the diagonal components of the Reynolds stress tensor. But how is this energy? This is, it is giving me meter square per second square. Exactly, per unit mass, right? I need this. So this is per unit mass. Turbulence, this is per unit mass. Okay, so this will give me joule, kg meter square per second square. Okay, so by definition this is your turbulence kinetic energy. So we need an equation for it because energy is scalar, right? So one way of looking turbulence is also that I don't want to look it as directional dependency in anisotropy. I would like to look it as turbulence energy, K. For that it is straightforward if you have Reynolds stress equation, because you see I need ui prime average, so I need to simply contract the indices, right? So the derivation is straightforward. So start from Reynolds stress equation. Start from Reynolds stress equation, which is giving me rho by dou t of, I have ui prime uk prime, right? uk prime plus the advection rate of change of Reynolds stresses ui prime uk prime equal to, I have the diffusion rate, which is dou by dou xj of, I have this minus 1 by rho p prime ui prime delta kj, okay, plus p prime uk prime delta ij, that is the pressure diffusion rate term, and then you have the viscous diffusion rate, which is plus nu dou by dou xj of ui prime uk prime, and then I have the last term, which is minus ui prime uj prime uk prime, the triple velocity correlation term, transport due to turbulence itself, the turbulent diffusion rate, viscous diffusion rate, and the pressure diffusion rate. Okay, I have simply taken the divergence term out here, dou by dou xj of these three. We have already derived this. Then I have the pressure strain rate term, which is plus p prime by rho dou I prime by dou xk plus dou uk prime by dou xi, and then I have the production rate term, which is minus of, I have uk prime uj prime dou ui bar by dou xj plus ui prime uj prime dou uk bar by dou xj. Okay, and finally the dissipation rate term, which is minus 2 nu dou ui prime by dou xj dou uk prime by dou xj. This we have already derived, the transport, right, the diffusion rate, the redistribution rate or the pressure strain rate, production rate, and dissipation rate. So the equation is ready. Now all we have to do to derive this so-called turbulence kinetic energy equation is contract the indices, set I equal to k. Okay. So by contracting the indices, that is setting I equal to k, what do I get? I get dou by dou t of ui prime over bar plus uj bar dou by dou xj ui prime equal to dou by dou xj of, now if I set I equal to k, I get 2 times of this, so I get minus I equal to k, so I just need to write down one of the term, so I get minus 2 by rho p prime ui prime dou ij, right, dou ij I equal to k, yes, delta ij term, plus I have the new dou by dou xj of ui prime over bar minus ui prime uj prime. I and k we are contracting, setting I equal to k, right? So I prime and j prime. Okay, and then I have the pressure strain rate term. So p prime by rho dou ui prime by dou I equal to k becomes dou by dou xi, 2 of this dou I prime by dou xi, dou I prime by dou xi. What happens to this term? Dou I prime by dou xi, what is it? By continuity it is 0. So you see, that's why I discussed the role of pressure strain rate in the context of Reynolds stresses, because when it comes to turbulence kinetic energy equation, this term is gone. This does not mean that redistribution is active. It's just that turbulence kinetic energy is a scalar quantity. We are trying to reduce studying turbulence as a scalar, and obviously we are going to have some loss of information. Redistribution is active at the stresses because the turbulence kinetic energy definition you can see here. It is a sum of 3 stresses. This redistribution is active when these 3 are being computed, right? And the sum total is only the turbulence kinetic energy, but in the equation that term goes away, the redistribution rate goes away. So modeling community will be happy, right? So if less terms means much better, and therefore the beginning of what you call the k based models, k epsilon, k omega, you would have heard about these names. So obviously you would like to start with an equation with less number of unknowns. So given Reynolds stress equation and turbulence kinetic energy, you would say turbulence kinetic energy because it has less unknowns. But remember that you are going to have some loss of information by looking into turbulence as a scalar quantity. Okay, you lose this anisotropic nature, study of the anisotropy. So this term is gone due to the continuity here. The pressure strain rate term, an important term, and then the production rate. So it's minus. So since I is setting equal to k, this is minus 2 of this, minus 2 of its ui prime uj prime dou ui bar by dou xj. Okay, the production rate of turbulence kinetic energy here, not the stresses, and the dissipation rate, which is minus 2 nu dou ui prime by dou xj, dou ui prime by dou xj, it is squared now. You see now, more terms are going to make sense what each of these terms are, right? So now the definition is turbulence kinetic energy K is half of ui prime bar, but now I have an equation for the twice of that. So let's divide throughout by half also. Okay, so setting I equal to K and dividing throughout by 2. Each term we divide it by 2, so I get half of this, right? So I can introduce here half, same thing here. This, if I do it here, half of this, 2 here by 2 here, half here, so these two terms goes away. So giving me, since half is a constant, I can just move it inside the derivative. So I simply get this as dou K by dou T plus, same here, half is moved inside the derivative. So I get uj bar dou K by dou xj. Now I am getting a transport equation for turbulence kinetic energy. So I have now dou by dou xj of, right, it's p prime ui prime by rho delta ij plus nu, half again goes inside the derivative, making it dou K by dou xj minus half ui prime uj prime. This is the diffusion rate of turbulence kinetic energy. This term is gone. So I have minus ui prime uj prime. This is the production rate of turbulence kinetic energy, and then the dissipation rate of turbulence kinetic energy, ui prime by dou xj squared average. So this is your equation for turbulence kinetic energy. Okay, so where this is the diffusion rate of turbulence kinetic energy, this is your production rate of turbulence kinetic energy, and this is the dissipation rate of turbulence kinetic energy, which we use sometimes also called as epsilon. Okay, the dissipation rate, this is the dissipation rate of turbulence kinetic energy. This is also symbolically used as epsilon term. This entire term is epsilon. Okay, so some of you would have heard of this model, k-epsilon model. So where k is this transport equation for k, epsilon means the dissipation rate of turbulence kinetic energy. Okay, so this is the epsilon term here. This particular term is epsilon, dissipation rate of turbulence kinetic energy.